Exponential functions. India is the second most populous country in the world with a population in 2008 of about 1.14 billion. The population is growing by about 1.34% each year. We might ask if we can find a formula to model the population P as a function of time t in years after 2008 if the population continues to grow at this rate. In linear growth, we had a constant rate of change, a constant number that the output increased for each increase in input. For example, in the equation f of x equals 3x plus 4, the slope tells us the output increases by 3 each time the input increases by 1. This population scenario is different. We have a percent rate of change rather than a constant number of people as our rate of change. To see the significance of this difference, consider these two companies. Company A has 100 stores and expands by opening 50 new stores a year. Company B has 100 stores and expands by increasing the number of stores by 50% of their total each year. Looking at a few years of growth for these companies, notice that with the percent growth, each year the company grows by 50% of the current year's total, so as the company grows larger, the number of stores added in a year grows as well. To try to simplify the calculations, notice that after 1 year, the number of stores for Company B was 100 plus 0.50 multiplied by 100, or equivalently by factoring 100 multiplied by 1 plus 0.50 equals 150. We could think of this as the new number of stores in the original 100% plus another 50%. After 2 years, the number of stores was 100 multiplied by 1 plus 0.50 multiplied by 1 plus 0.50 equals 100 multiplied by 1 plus 0.50 squared equals 225. After 3 years, the number of stores was 100 multiplied by 1 plus 0.50 squared multiplied by 1 plus 0.50 equals 100 multiplied by 1 plus 0.50 cubed equals 337.5. From this, we can generalize, noticing that to show a 50% increase, each year we multiply by a factor of 1 plus 0.50. So after n years, our equation would be b of n equals 100 multiplied by 1 plus 0.50 to the nth power. In this equation, the 100 represented the initial quantity and the 0.50 was the percent growth rate. Generalizing further, we arrive at the general form of exponential functions. Exponential function. An exponential growth or decay function is a function that grows or shrinks at a constant percent growth rate. The equation can be written in the form f of x equals a multiplied by 1 plus r to the x power, or f of x equals a b to the x power, where b equals 1 plus r, where a is the initial or starting value of the function, r is the percent growth or decay rate written as a decimal, b is the growth factor or growth multiplier. Since powers of negative numbers behave strangely, we limit b to positive values. To see more clearly the difference between exponential and linear growth, compare the two tables and graphs below, which illustrate the growth of company A and B described above over a longer time frame if the growth patterns were to continue. Example 1. Write an exponential function for India's population and use it to predict the population in 2020. At the beginning of the chapter, we were given India's population of 1.14 billion in the year 2008 and a percent growth rate of 1.34%. Using 2008 as our starting time, t equals 0, our initial population will be 1.14 billion. Since the percent growth rate was 1.34%, Our value for r is 0.0134. Using the basic formula for exponential growth, f of x equals a multiplied by 1 plus r to the x power, we can write the formula f of t equals 1.14 multiplied by 1 plus 0.0134 to the t power. To estimate the population in 2020, we evaluate the function at t equals 12, since 2020 is 12 years after 2008. f of 12 equals 1.14 multiplied by 1 plus 0.0134 to the 12th power, approximately 1.337 billion people in 2020. For comparison, the actual population of India in 2020 was about 1.380 billion. Try it now. Given the three statements below, identify which represent exponential functions. A, the cost of living allowance for state employees increases salaries by 3.1% each year. B, state employees can expect a $300 raise each year they work for the state. C, tuition costs have increased by 2.8% each year for the last 3 years. Example 2. A certificate of deposit, CD, is a type of savings account offered by banks, typically offering a higher interest rate in return for a fixed length of time you will leave your money invested. If a bank offers a 24-month CD with an annual interest rate of 1.2% compounded monthly, how much would the $1,000 investment grow to over those 24 months? First, we must notice that the interest rate is an annual rate but is compounded monthly, meaning interest is calculated and added to the account monthly. To find the monthly interest rate, we divide the annual rate of 1.2% by 12 since there are 12 months in a year. 1.2% divided by 12 equals 0.1%. Each month we will earn 0.1% interest. From this, we can set up an exponential function with our initial amount of $1,000 and a growth rate of r equals 0.001 and our input m measured in months. F of m equals 1,000 multiplied by 1 plus 0.012 divided by 12 to the m power. F of m equals 1,000 multiplied by 1 plus 0.001 to the m power. After 24 months, the account will have grown to f of 24 equals 1,000 multiplied by 1 plus 0.001 to the 24th power equals $1,024.28. Try it now. Looking at these two equations that represent the balance in two different savings accounts, which account is growing faster and which account will have a higher balance after 3 years? A of t equals 1,000 multiplied by 1.05 to the t power. B of t equals 900 multiplied by 1.075 to the t power. In all the preceding examples, we saw exponential growth. Exponential functions can also be used to model quantities that are decreasing at a constant percent rate. An example of this is radioactive decay, a process in which radioactive isotopes of certain atoms transfer to an atom of a different type, causing a percentage decrease of the original material over time. Example 3. Bismuth-210 is an isotope that radioactively decays by about 13% each day, meaning 13% of the remaining bismuth-210 transform into another atom, polonium-210 in this case, each day. If you begin with 100 milligrams of bismuth-210, how much remains after 1 week? With radioactive decay, instead of the quantity increasing at a percent rate, the quantity is decreasing at a percent rate. Our initial quantity is A equals 100 milligrams, and our growth rate will be negative 13% since we are decreasing. R equals negative 0.13. This gives the equation Q of D equals 100 multiplied by 1 minus 0.13 to the D power equals 100 multiplied by 0.87 to the D power. This can also be explained by recognizing that if 13% decays, then 87% remains. After 1 week, 7 days, the quantity remaining would be Q of 7 equals 100 multiplied by 0.87 to the 7th power equals 37.73 milligrams of bismuth 210 remains. Try it now. A population of 1,000 is decreasing 3% each year. Find the population in 30 years. Example 4. T of Q represents the total number of Android smartphone contracts in thousands held by a certain Verizon store region measured quarterly since January 1st, 2016. Interpret all the parts of the equation T of 2 equals 86 multiplied by 1.64 squared equals 231.3056. Interpreting this from the basic exponential form, we know that 86 is our initial value. This means that on January 1st, 2016, this region had 86,000 Android smartphone contracts. Since B equals 1 plus R equals 1.64, we know that every quarter the number of smartphone contracts grows by 64%. T of 2 equals 231.3056 means that in the second quarter, or at the end of the second quarter, there were approximately 231,306 Android smartphone contracts.